All right, well, I still don't know who the President of the United States is, so if you stay up all night waiting for that, you're still up. Wednesday, November 4th, 2020. Physics 174, the 11 a.m. class, starting now. So, plan so far. Keep our eye on the prize here. Exam number 3. It's in 2 weeks. Wednesday, November 18th. Right, makeup exams. 2 weeks from Friday. And I need to email these folks, or probably what happens, they probably email me and just got stuck in it sank to the bottom of my inbox. It happens fast sometimes. Hopefully the final. That's the goal for a Monday final. Before Thanksgiving. Why not end a very unusual year with an extremely unusual final? Have it before what was usually Thanksgiving break. Today, examples in the work kinetic energy theorem. And there's a worksheet on Canvas now. Hopefully, everybody else has got it. I know you guys should have it, but whether or not I click the button to make it viewable, that's another question. So look all the way down your Canvas site, and it should be called today's day, 11:04 to something, probably work. You know, blah, 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 blah. Okay, so let's look for that worksheet down at the very bottom of it. I know it was on there because I put it on there and then I realized I had the wrong date. I had 10/04/20. I still think it was October. So I had to go back and correct all the 11, but that doesn't mean it's still activated. It's just, it's there, but you can't see it, which is useless. So tell me if you can't find it eventually. There's going to be one big difference on the current worksheet or the previous worksheet. Skip the non-constant forces problems. We'll do non-constant forces, but only for a very specific case, which is nonetheless very practical. We'll limit ourselves to a specific type of non-constant forces, and that's going to be the springs. So I'll have to restructure. I just won't even, I don't think anything in that worksheet under the heading of non-constant forces is applicable anymore. So I'll make up some new stuff, and I'll give a general derivation of it on Friday. So this is going to be a Friday topic. If you did look ahead, or I've mentioned it too, non-constant forces deals with integration. Some of us just haven't got there yet in math, or a little fuzzy on it, so I had to explain integration, kind of like how I did derivatives. But integration, even though it's reverse of deriving, it can get a little bit tedious at times, or a little bit, so it seems like it's a little hard to see that pattern. So that's probably for the best, and we're running out of time. I'd rather not spend time doing calculus class. I'd rather spend time doing physics. So I'll derive the spring equation. I think that's what my goal is going to be now. It will come, if I do the full-blown calculation, it will come with integration. And you may think, oh no, but if you haven't worked with springs, what will happen is I'll use integration to get the a nice equation, and then that's the equation itself dealing with the work or energy storage in a spring was derived from integration, but it has no integration in the final formula. So if you haven't seen it before, don't panic. We'll get something, we can box it, and we'll be fine. So even if you don't understand exactly how it got where it was, just take my word for it. It actually works. So, so that's what we'll do on Friday. And that'll finish up chapter 7. Now, whether or not we'll have enough time to do examples, and I do examples, probably not, but we'll finish up the meat and potatoes of chapter 7 on Friday. By Monday, we'll wrap it up with the, you know, like we're doing today with examples of the work kinetic energy theorem after I discussed it in class on Monday. And then we'll start chapter 8 on Monday of next week, which will be the conservation of energy chapter. Yeehaw. I think I'll be able to get conservation momentum. It's a pretty quick, not that big a deal. It's big a deal, but it's not exactly a hard concept to get. And we're quite in the semester around that topic. Now on you guys for the 11 o'clock class, I did an example of a car skidding to a stop and figuring out the initial speed of it. The police would be very interested in an accident scene and whether or not the driver was speeding. You ask a driver if they were speeding after an accident, they always invariably say, no, I wasn't. And that's when you bring in the physicist, and we're the experts, and we're brought in the court cases, and we do the same thing we do here in class. We use we use conservation of energy along with frictional forces, and we figure out if the person was actually telling the truth, or maybe they were just accidentally mistaken. But we did that. So the other classes did that this morning. You guys did it on Monday. So what we're going to do is we're just going to jump right into the examples. So you want to grab this worksheet here, virtually at least. And the first two problems, I mean, there's 3 problems I think total that don't deal with the kinetic. Yeah, the first 3 just deal with the work and scalar dot product review, because we're just coming off of it. If you can't do this, you'll have trouble probably doing this perhaps. And then we got the work kinetic energy theorem problem sitting back here. There's lots of them, but we're only going to concentrate on do 1, 2, 4, and 5. That's what our goal is. Okay. So make sure you get online, get it. If you're here in class in front of me, grand total of 2 people, I can hand out you a virtual copy or an actual hard copy of it. Yeah, Drew. I got Drew and Andrew. Where's your compatriot at?
Well, calculus canceled.
Cancel? What happened to calculus?
I don't know.
The election? Disappointing the election result? Hey, you can't be disappointed. It's still going on. It's a gift that never stops. Elections? Yeah, it is. I actually like watching big words and stuff like that. I like watching people get paid to actually do nothing but sit around and talk. That's what my dream job. It's like a sports commentator. I mean, you know, what could happen? Well, let's just say what happens, but they got to fill that. And the longer it drug on, the more they had to talk, and it gets kind of comical after a while. I mean, they're talking about just the most useless of stuff, and it's like, and they're getting paid for it. And you're like, well, come to physics class. I can yak too. I don't cost that much either. Oops, I just unconnected something. What was that one? Power cord. All right, so work on these babies. I got some people saying some people in class. I got to wander around maybe occasionally if they need some help. Otherwise, if you want to unmute Mike and say, hey, I can't quite get going on this one, I understand. I'll come back and get you. The first problem, number 1 and 2, the big problem is actually there's a few little things you got to figure out, but the big problem is find those angles, the correct angles you need. It's a lesson in geometry, which, as I said, generally the work calculation is the hardest thing is figuring out an angle. So see if you can get it, and that's your problem usually. I'll just sit back and wait for the questions. I'm going to step out of the room for a moment. I've got to get a protractor involved as well.
Just get a crowbar. Yeah, I didn't realize that the force was being applied at a 7-degree angle.
A nice easy angle, is that what you were talking about?
No. Yeah.
Yeah. Here's the horizontal, second one's horizontal. The angle being brought in, Drew, did you get the angle? I haven't gotten that right yet. Dang it. How about we just start this off here? Can't find the worksheet. There, I just found it. Okay, I worked that well. I answered their own question. I like that when I see that. Well, I can't believe I found a protractor and all this stuff up here. Okay, I'm gonna hit and do this first one here. Try to get it going. This angle I drew here is a horrible angle, and so when I try to draw the correct angles, it's not to scale, or it just doesn't look right at all. So I'm gonna have to try to draw this freehand a lot better than I did here. This is definitely not a 56-degree angle. It's much closer to a 30-degree angle if I eyeball it. I mean, it's definitely getting bigger than a 45, and a 45 you got to be somewhere up in here. So, okay. This is the one I promised you guys I'd give you. I said, oh, you know, I was feeling bad. I figured out delta R, the displacement, and it was always looking like R final. It was because it always started at the origin. I said, well, I'll give you one that doesn't have to start at the origin, and forgot about it on Monday. Here it is. Got this thing finally. So if you write a little bit to the side here. I guess it'll be officially page 2. So delta R always equals R final minus R initial. No matter if I do method A or method B on the next page, I've got to get my delta R, and it's not here yet. Soon will be. So your final position is going to be 3.3 I hat plus 5 J hat minus R initial, which is 2 I hat plus 3.0 J hat. So you subtract out the initial position from your final. So 3.3 minus 2 is just 1.3 I hat. And 5 minus 3, last I checked, is just 0.02 J hat. Okay. Now, this is going to be useful in B, because we're going to need to know the displacement vector in terms of its components. You're getting there, but you're not done if you're going to use method 1. You need the magnitude. So delta R magnitude is going to equal your x component plus your y component. I'll put a big 0 here for your z components. Sometimes it's there, sometimes it's not. I don't want you forgetting that. And let's see how it's. Delta R equals the square root of 5.69. Oops. Let's see if I can write a 6 the way it's supposed to be. You can calculate that up if you want, but it's as far as I know, it's a non-terminating decimal, so you'd have to round, and rounding sometimes gives us a few little errors here, which is no big deal, but it's easier to write that anyway, so I'm just going to keep my delta R as this. I can plug it in down here. I also know my magnitude of my force. It's going to go there. That guy's going to go there. The problem is finding this theta, and this forces at some really weird angle, it looks like. So let's try to figure out the angle we need. I think let's try to draw it the way it's supposed to look, or at least get better at it. Need theta. And this is the angle between F and delta R. So I had to draw those two vectors in there. I don't care if the length aren't the scale. I just care if I got their angles at least looking decent here. So let's see. Here's my base. I got 56-degree angle, huh? Well, that's 90. That's a good guess. Oh, lower. Ooh, that's steep. That's 56 degrees. Let's see. That's my normal, the incline. And I need to draw 70 degrees relative to that guy. Okay, so there's 90 for him. Something like that. Yeah, that doesn't look too bad. Looks better than I got. Okay. So this is the way that it's drawn. So this 10.5 newtons, I guess I should probably draw it like this. I would draw it like that, but actually there's going to be some angles in here, so I got to keep it away. So this should be a vector with a magnitude 10.5 point along that arrow right there. Okay. Now what's my delta R? My delta R is moving up the ramp. So this is where I start. This is my mass right here at the starting point. And this is where I end up. Delta R. It should lie along the ramp exactly, but it's made it hover above it there. So I think, you know, look back. Hey, wait a minute. There's only, I drew two things. There's only one line. Well, the two lines are on top of each other. So I drew one just slightly above it. So don't panic about that, please. And when we try to find the angle between two vectors, we draw them tail to tail. So this one's actually going head and then the tail. So what I want to do is I want to slide this vector over so that it points in the same direction. And technically it has to have the same length, but really I just want to know the same direction because I'm trying to find the angle between the two. And to do that, that's why I drew the line extended. I'm just going to slide that old vector over here where this is equal to F. I mean, imagine if you're trying to push a ball or a mass up a ramp with this force, you could accomplish the same thing if you can go on the other side of the ramp. And of course, you'd have to have a groove there. You say, well, I'd be underneath the ramp. I wouldn't be able to get, yes, you're right. But if you do like a magic trick and have a groove here and you're hiding in here, you can pull on the mass, pull in the same direction with the same magnitude, and the mass itself won't know the difference. It'll go up the ramp just like if you were pushing it. So pushing it and pulling it will have the same effect as far as the direction it would move up the ramp. It may change the frictional force, but that's not the point right now. All right, so now we want to find this angle right here. Okay. That's what we need. All right, so, and let's see what we got. We know this is 70. And this is 56, but definitely this angle is not 56 degrees. This is, that's 56 degrees. Okay. Anybody know what the angle is going to be? Excellent drawing up there.
20.
20. You're just guessing, aren't you?
No.
The lucky number, that's right. It's 20 degrees. And there's probably a few ways to do it geometrically, but here's the way I'd do it. This line right here is your normal line to the surface of the ramp. So on this side, it's 9 degrees. On this side, it's 9 degrees. So all the way from this line down to here is 90. I know this angle is 70. So this guy right here must be 20 degrees. This is 90 minus 70 equals 20 degrees. My son just took a geometry test last week, when we were studying for it, oh, there's all these geometrical proofs. Oh, you know, interior angles of a triangle equals 180 degrees. And a lot of them, I still kind of remember what they are, but I don't know the names of them anymore. There's one, I said, there's one of them I always use, or I use a lot in physics, and therefore I know it. Opposite vertical angles are equal to each other. In other words, if you draw two straight lines and you intersect it, if those two straight lines intersect each other, and there's a lot of lines coming up here, but I'm talking the line made by the ramp, where the delta R is, and the line made by my force, just extending it, then this angle here equals that angle there. And that's my theta. So this guy equals 20 degrees. Whew. That's a lot of work to get that 20-degree angle. Well, like I said, the angles are the bad guys. So work equals, remember, FR, F delta R cosine theta, equals 10.5 times my magnitude of my displacement, square root of 5.69 times cosine of 20 degrees. And that should give it to me. So 23.5. If I kept my force in newtons, which it was, given here as newtons, and I had my delta R in terms of meters, which it said when I did it, my position was in meters. Then I'm a happy camper, and I know my units of work should be joules, Newton times meters. That's that guy. All right. That's a fun one. Now let's do part B. So this guy, to do this one, you have to know the force in terms of its x and y components, and so you have, and so much you know for the displacement delta R. The good news is we have delta R vector, displacement vector. Already found him. I found him right there. So we know him. But we need vector F in terms of its x components, y components, and we just want to, for the fun of it, it's z components, and it has not, because of 2D case here. All right, so well, guys, remember how you figure out the x component of a vector? If you know its magnitude, we know the magnitude of this vector, it's 10.5. So if you know the magnitude, how do you find the x component? There's all kinds of little ways you can do it, but what's our standard bread and butter? Go back to chapter 2, this is what we're always trying to do. Drew? The triangles, yeah. We're talking for 2D case. If you've got this to be vector F, its magnitude, its hypotenuse 10.5. We want the y component. We want the x component. And to do that, we need to know this angle right here. It's just, it's going to be F cosine theta equals F sine theta. Sorry, kind of ran over the page there. So drat, we got to find another angle. Now this method here is really great if we were giving the displacement in terms of, my bad, I wrote that 1.3 j hat is a lot of j's, I guess, today. If we knew our displacement in terms of I hats, j hats, and k hats, as well as F. This would be the go-to guy we do it for work. It's just a sum of three products. Without that equal sign right there. Bad cut and paste from me. But we don't know vector F, so we got to figure it out as far as its components go. So the question is, what's that angle? Ooh.
36.
36 is the right answer. Ding, ding, ding. Looking back at previous drawing. So I'm going to replicate some of this thing right here. That's the ramp. And let's see, I got the first going in like that. That's the 20 degrees. These very sloppily drawn lines here are parallel to the x-axis, parallel to the x-axis. I know we usually we like to stick that x-axis on the bottom. It's just common in human nature, but there's no absolute, there's nothing written in the Constitution. Your x-axis has to be on the horizontal on the floor. It's just a line which is horizontal. I can put the positive x-axis up here. I can put it down here. As long as it's horizontal, I'm fine. So if my triangle's up here or this bothers you, just slide the whole shebang right to the bottom. You can act like I'm pushing the mass at the very base of my incline, and then the whole problem would be set with it relative to the base for your x-axis. Otherwise, you got to slide it up and make a new dashed line. I think based on the last drawing, hopefully you're okay with me saying, this is 56 and that's the 20 we figured out. Now, I want the angle. Now, this is the crazy thing about the these work equations. Remember on the first one we did, first part, we had to find the angle between delta R and our force. Oops, delta R and force, which was the 20-degree guy. When you're breaking things into components, you want your angle relative to an axis, because we're breaking it down into the x component and the y component, specifically the x if you can. Otherwise, you got to worry about your cosine sine being mixed up. So in other words, we want that angle. Matter of fact, since I called that theta over here, watch what I'm about ready to do. I'm going to call this theta F and that theta F. And that's because I don't want you looking back at A and saying, well, these thetas are different. They are different. They're two different angles. So I'll give them two different names here. So you won't start thinking, oh, why aren't they the same? They're not the same angle. All right, so 20 plus theta F equals 56. Theta F equals 36 degrees. Okay. So with that, you can find your force in terms of its components. It's the magnitude of the force times cosine 36 degrees, I hat, plus magnitude of force sine 36 degrees, j hat, plus 0 k hat. There's nothing out here. And let's do the intermediate steps. I didn't do the intermediate steps last time. I still had a rounding error or rounding deviation. So let's keep the numbers and let's round them, see what we get. Most people like to do these steps anyway, one piece at a time. This is 8.5 I hat, not exactly, but I rounded. And the other guy is 6.2 j hat. Now you're ready to rock and roll. We've got vector F, and we have vector displacement vector delta R in terms of I hats and j hats, k hats which are 0. So we can use this equation up here now. Work equals Fx delta Rx plus Fy delta Ry plus Fz delta Rz In case you didn't catch it, hopefully you figured that out. That equal sign with me is a bad cut and paste, so be sure to remove that or blotch it out. I do that because if I use Word, I have that subscript sitting there and I cut and paste it, not including a symbol, then it will, I'll have to start off on subscript. I gotta click it up, so it's being lazy and it costs me dearly. Hey, plug in your numbers. Fx is 8.5, x component for your force. What's the x component for my displacement vector? What's that guy right there? 0.3. Plus the y component for my vector f, force vector, 6.2. And then finally, times the displacement vector's y component. This comes out to be, it's a rat, still won't round right, but okay. 23.4, and what should be 3.5. I wouldn't worry about that. I mean, if you get something like that on a multiple choice test or whatever, and that's, you know, you should feel real good. Give yourself a pat on the back. If you do it, you've done a few rounding errors, and you think, oh, hey, look, the answers are all like in the 20s, and I got 8.9 for my answer. That's not a rounding error. So go find out what happened there. Okay, there's that guy. Now let's see if you guys can do, well, number 2. All right, I'll leave you alone. Other than I think I should give you a warning right off the bat. Number 2 looks like a bear. Woo-hoo. But keep your eye on the prize. There's a lot of stuff in here, and a lot of it's useless, or it can be used, but oh, it's a horrific equation to do it. But just find out what you're solving for, and say, okay, what equations do I have that can help me out? And then what do I got? Which one will hopefully be the easiest one to work with? Right? So I'll let you stew about that for a moment, and we'll go from there. Yeah. Concede defeat early on. All right, so here, how do we get the work? What are we trying to find? Well, the goal is, like I said, keep your eye on the prize. We're trying to find the work done by good old F1. So give yourself a little subscript there so I can keep track of, you know, just the variables. We can find work 3 ways. We can find it with the work kinetic energy theorem, which is coming up, so you probably guess we're not going to use that. We could actually do it. That's actually the painful one. We can do that with this guy, but it's got so many. Well, it's only got 3 forces in it that we have to worry about. But there's several angles and distances. You got, you know, the distance is already known, but that gets a little scary with all the numbers. And you also got to use the kinematic equation to get, I think, acceleration out of it. Ugh, it's bad. But if we just want to find the work done by F1. That's F1 delta R cosine theta 1 equals, or this is another way of writing it, F1x delta Rx. This is a scalar product, your scalar dot product. F1y delta Ry plus, if we've got it, and it's not going to be the case in this problem, F1z delta Rz. Right? This guy, we did both of them in that last example. This is your go-to guy if you know, I mean, we didn't have this in the last one. We didn't have anything to make it easy for either method. We had to figure stuff out. But this one you run right to immediately if you know the components of vector F and vector delta R, your displacement. So if you're given this guy forces in terms of I hats and J hats, and same way with delta R, you run into this one. This is your guy with open arms. Otherwise, like we did the last time we could do it, we had to figure out a few things, and that was the figuring out the force vector. This guy, you'd be really inclined to do this if you know, you don't know the vector component, but you know the magnitudes. So which one do you know? Do you know the components or do you know the magnitudes? Know the magnitude. So I'm guessing that my first gut impression would be run and try to use this guy right here. Maybe we'll have to do what we did in the last problem, though, in part B, and find the components. But a minute, if you know the magnitude, you're only off an angle from getting this guy. So W1 equals F1, which is 4,800 newtons. It's this guy right here. Times the distance it moves, the displacement, and that's 3 meters. That's how far it's moving. Now we gotta get cosine. Cosine is going to be or cosine theta, where theta is the angle between our displacement vector, delta r, which is a long ramp, and our force. And our force is told to be horizontal. So I want to write it like that. This is the angle I want. Now, extend this down a little bit. There's my whole ramp. This is 30 degrees. Anybody like this is geometrical proof here. I forgot I know it's right, but I forgot the name of it. Interior angles, opposite interior angles, maybe, or something like that. Does anybody know how this 30 degrees relates to that theta?
It's the same.
It's the same. This guy's the same. So this is 30 degrees. Think. And so you're just off by an angle, Drew. I'm guessing that's what you did. So. There's your answer. So a lot of stuff up here, and that's, I mean, let's face it, in life you're going to be dealt with that. You're lucky if you got everything you need, but you're going to be confronted with a lot of stuff maybe you don't want at all, and so you've got to sift through it. That's actually one of the reasons they make you take physics class. Usually, with the guys, you got to sift through it, know what you're solving for. It's a logic puzzle. What do I want? What do I need? How do I get it? Or is it already there? What do I ignore? That's like kids a lot. Which ones do I ignore right now? No, I never ignore your kids. All right, so that's 2. I'd say we do number 3. We only got like 25 minutes. I really definitely want to make sure we get to the work kinetic energy pair. We can always come back. Let's do this guy first. The order I just threw it together, and then after I started working with this in the morning class, the earlier class, it'd be better to do it this way. This one right here, number 5, is a lot easier. Or in my opinion, it's a lot easier. If you get the other one, that's great. But it's got a lot fewer steps. So that's usually better, bodes well for easier. So this is the work kinetic energy theorem. So that's a clue. I'd be using that. And if you say in life, how do you know if it's work kinetic energy theorem? Actually, when you do the conservation of energy equation, that'll embody a lot of this theory right here. So probably just use that guy. But as far as what do you know to look at, one thing, how would you know this has probably got something to do with work? That's always a key. Well, where do I start? I mean, let's face it, you're looking at an exam. You know, you got your book and stuff like that, but still it's a big old book and lots of notes. And how do you know this guy even deals with work?
So,
It says work. I mean, if it says work, or J for joules, maybe if it didn't say work, I'd be thinking, oh, energy, maybe work. So it's definitely work is up here, and there isn't much information. So it's probably not a lot of superfluous stuff here, unlike the last one, which was like a paragraph. It literally was a paragraph with a bunch of stuff. Oh, some math is coming in. So when it comes to doing this guy, we deal with work. As far as the kinetic energy theorem, work kinetic energy theorem, what can you get out of the work kinetic energy theorem? What variables are in that work kinetic energy theorem? Looking right at you, Drew. You've already answered one. How about you, Andrew? You're over the computer.
Mass and velocity?
Yeah, actually, it's just speeds. Actually, it's even better than that. But it's speeds. It's velocities if you want to, if you know the direction, but definitely a speed. So if you're trying to find speeds and you're dealing with, you see work involved there, and this is one way of attacking it. In the problem number 4, you'll see us solve for something else. We'll be given the speeds, and we'll find the distances. So if you feel like, oh, here's distance and there's work, and if you're involved with distance, work, and speeds, you know 2 of the 3, you want to find the other guy, I'd be thinking work kinetic energy theorem. So in other words,
So could you set it to like K1 equals K2 and then solve for the missing variable?
well, that's all you can do that. I'll say I can do that, but we won't do it in this case. So W net, you say set K1 equals a K2, that'd be a K final minus K initial. Well, you only set K initial equal to K final if the W net was 0 in it. So it's not going to be 0. And it's not 0 because it's told up here to be 160. So this left side is going to be equal to a non-zero number. Does that make sense? A lot better? Oh.
Maybe we'll just solve it.
Okay, just hold on tight now. All right, so W net, does anybody know what W net is here? The work net on the object?
160.
Yeah, 160. I know it doesn't say that, but this is how much work is done on the mass. So, I mean, this is like if someone pays you $100, that's the total bill. You figure you don't have somebody specify. If someone's talking to someone and I hear someone say, "Oh, I was paid $100 for my work," I would assume that means that was a total bill, unless they're griping about they only got partially paid. So you see it's 160 joules. This is the total work done on it. It would have to be specified if it's not. I mean, it would have to be, the gravitational force does 160 joules on the object. If it's just hanging out here, this is how much work is done on the object, and yeah, that's definitely your W net. And usually this is like a placeholder equation almost. I call it a placeholder because we usually just use it temporarily and we want to get to something else with a little bit more information on it. You could be asked for a delta K or maybe a K initial, K final. Sometimes it has relevance, but usually we're trying to find like a speed. And you want to find speed with a work kinetic energy equation, you've got to expand these guys to write it like this. So what do we know? Well, we want to find this guy, and we know the masses. We know the initial, that guy right there, and we know we've already stuck in work net. So yeah, we can solve this guy. So let's see, do a little bit of mathematical manipulation here. Get this guy all by itself for a second. So I multiplied both sides by 2 over m, by canceling these guys as m over 2s and sticking it over here. Getting the final speed all by its lonesome. Oh, 2 times 160 is 320. I'm not going to write 2 times 160 again. So over the joules over the mass at 5 kilograms. So I can put the units in here just for the fun of it. Plus V initial squared V final equals 320 over 5. I'll drop the units now. Like that. 6 squared. V final, 320 divided by 5 plus 36. Hey, square root of 100. Ta-da! It's like a magic trick. Just know it's fun. Sorry, I dropped some stuff. So you can kind of see where we, why it's this energy thing's pretty good to investment, at least if you're, if you're not in that area, but you can see where we'd be really interested in physics. We could have done this. Let's see, I don't think we got enough information. Had some other stuff we had to give, but you remember trying to figure out the final velocity of an object. If it was, we had to set up our, our scorecards, and boy, if it's at an angle, we'd have to do 2D motion, and we had to solve for the x and the x final and y final, and combine them at the end to get our speed. Now we can't tell you if it's, we can only tell the speed, or we can't get individual, can't get vector components, which is sad, but nonetheless, we can get our final magnitude of our speed with a very simplistic equation. And I say simplistic, it doesn't deal with vectors. And this is something that's mathematically not hard to do, but it's just maybe a little bit different to us. But anyway, this is a easier way to get some of the stuff we got earlier in chapters 3 and 4. That's why we like to do it. And also, anyways, it's sometimes a way to do something which we don't have the information to solve it with kinematics, with equations of motion. All right, so any question on that, guy?
No.
No. Oh, no. Okay, well, I guess we'll flip to 4 then. Yeah. Okay, so this one right here is trying to figure out how far the block will go up the incline, which this is Newton's second law. We could do it with Newton's second law, but we can also do it with this one. So show us we can go both ways. So if you didn't like using those force tables, you still got to use a little bit of a force table to get some stuff out of it, but you don't have to use full-blown Newton's second to get the acceleration. And from the acceleration, you go back and use equations of motion to get the distance that goes up the ramp. So it's, of course, on the exam, you can do anything you want to. So whatever if you think, well, I like this versus the other one, I'd go the other way. Uh-oh. Somebody just, sorry, the laptop died. I guess they're gone. I can't see them anymore. But yeah, somebody just emailed me, said their laptop battery died, or mail. I guess they went with their phone. All right, so let's run through this guy. So the question is, how far does it go up the ramp? We're going to use the work kinetic energy theorem, which is going to be W net equals delta K. And we always use W net for delta K. Like I said, you can't see, you can mathematically, you could separate it out, but when it comes to measuring an object, we can't tell about, well, how far does it go up the ramp based on, force to F1 or the gravitational weight or the frictional force. It'd be a ratio if you wanted to, but it's we wouldn't think about that. We think these forces are all acting on this object, and we measure it, and we measure the distance it goes up the ramp. So we're interested in the forces which act on it. Each force can supply work or do work for our object, or work against us, or maybe no work at all. So the first thing you gotta do is draw those forces. Normal force, gravitational force equals mg. And as we're moving up the ramp, we also have a frictional force going down the ramp. Here we go. So this is kind of looks very familiar to what the first example I did in class, but I took the easy route. I was just on a horizontal surface. This one's gonna be a little harder, but that's what we're doing. We're building up. We did the easy guy first. You can look at that to help us out, and then we can go on from there. Okay, we're just on the ramp now. So it's going to be the work done by the frictional force. Let's just write in this little WF, plus the work done by the normal force, plus the work done by the gravitational force, equals 1/2 mv final squared minus 1/2 mv initial squared. Let's see, make sure. Yeah, so that's, and we know, let's see, we know the initial speed. We also know it comes to rest. this guy here is 0. Again, that's before. So what's the work done by the frictional force? Well, every time this always works the same way. Unless you want to find the work done by any individual force, your next step will be to insert the work equation down for each individual force acting on the object. So it's going to be, recall, like this is what I wrote in that first example. The work equation is F delta R cosine theta. So we have the frictional force times delta R. Let's eliminate that part right now. Our displacement is going to be called D on this drawing. So FF D cosine theta F plus the normal force D cosine theta N plus the gravitational force D cosine theta G equals negative 1/2 mv initial squared. Okay. First thing you do is find those angles. And then for us, oops, I'm running out of room and out of time. Let me start this, get this far. Maybe I should write the displacement in red. It kind of sets it apart there. So as I'm right here, might as well do this guy first. We want to know the angle between your gravitational weight and your displacement, theta G. This is a line parallel to the positive x-axis, which is the base of my triangle, my ramp down there. And this angle is 25. And this is a 90-degree angle. So this is going to be 25 plus 90 equals 115. So he's going to go in right there. Normal force is always perpendicular to the surface. So theta N equals 90 degrees. And he's going to go in right there, and we get that magic cosine 90. So this whole term here is just going to go away. We don't have to worry about it. The frictional force opposes motion. So that's going to be 180 degrees relative to how we're moving up the ramp. So this is as far as I'm going to be able to get right now. Mu Fn, that's the frictional force. Times D times cosine 180 plus FND cosine 90. He's gone. Plus, remember when it comes to the gravitational force, it's always mg. Your weight is m times g. D cosine 115 equals negative 1/2 mv initial squared. And that v, remember these guys are just speeds now. So I want to get D. I'm out of time, but I know mu. Hopefully mu is 0.15. D I want, cosine 180 is negative 1. I know the M is, oh no, I don't know the M. Oh no, guess what's going to happen, you think, to the M's? Somehow they're probably going to cancel. G, I know. Oh, yeah, really? Is it up there? Oh, point. I just said, I didn't see it. So it's there. The normal force would have contained the N, although it's canceled out. But okay, you can put it in there and be fine. So we know the mass, we don't have to worry about that. The only thing you have to do is find Fn. And unfortunately, you still got to use a little bit of a force diagram. Okay, and I've got to leave you with that, so I'm way out of time. So I'll try to finish it off, and or I'll finish it off in one of the classes and put the notes online from that class. And the last one, number 5, so it should be a lot easier one for you. This guy, I did him first, but he's the bigger guy. Right? Alicia, did you get the other one? Did you get number 5?
I started number 5.
Okay. Okay, I'm sorry, you went back to watch the show, huh? All right. You guys take it easy then. Have a good day. I got office hours today. Stop on by if you got questions. Otherwise, I'll see you down the road. Woo, start compiling in the meeting. There we go.